Welcome! In this session, we'll explore LeetCode problem number 1789. While the primary problem details are unavailable, we'll use general algorithmic strategies to tackle it. Let's dive in and see how we can approach this challenge systematically. The primary problem information for LeetCode problem number 1789 is unavailable due to the data being absent from the training dataset. Unfortunately, this means that the problem's metadata, description, examples, and constraints cannot be provided here. To solve this problem, I recommend visiting the official LeetCode platform using the provided link. There, you will find the complete and accurate problem statement, input-output specifications, test cases with explanations, and any additional constraints. LeetCode remains the best resource for understanding and solving this problem, as it contains the most up-to-date information. When facing a problem with limited initial details, it's helpful to start with a brute force approach. This method allows us to explore all possible solutions in a straightforward manner, ensuring that our solution is correct before we focus on efficiency. For example, we can iterate through every possible input or combination to verify constraints and outcomes. While this approach is simple to implement and universally applicable, it typically comes with a high computational cost, often growing exponentially with input size. This makes it impractical for large-scale problems, but it serves as a crucial foundation for understanding the problem and verifying correctness before moving on to optimization. Once we have a clear understanding of the problem through brute force, the next step is to look for patterns or properties that can simplify the solution. By analyzing constraints or examples, we can identify opportunities to reduce redundant computations. For instance, we might use data structures like hash maps or trees, or algorithms like dynamic programming and greedy methods, to streamline the process. Additionally, for problems with sorted or hierarchical structures, techniques like divide and conquer or binary search can be highly effective. These approaches allow us to narrow the problem space efficiently, often reducing complexity to O, n log n, or even O log n. However, they require a deeper understanding of the problem's structure and may not always be applicable to unstructured data. Given the lack of specific details for this problem, the most effective strategy combines the brute force approach with iterative optimizations. Starting with a simple solution helps validate our understanding and ensures correctness, while refining the approach based on identified patterns or constraints enhances efficiency. A key step in this process is uncovering the underlying structure or core constraint of the problem. For instance, if the problem involves graphs, techniques like BFS or DFS can be applied, while array-based problems might benefit from strategies like sorting or sliding windows. This balanced approach is adaptable to various problem types, allowing us to progressively optimize without losing sight of the problem's requirements. Each approach has its trade-offs, and understanding these is vital when designing a solution. Brute force is straightforward and ensures correctness, but it becomes computationally expensive as input size grows. Optimized algorithms, on the other hand, offer significant performance improvements, but they often require deeper problem insights and a more complex implementation. Divide and conquer or binary search methods are highly efficient but rely on the presence of inherent structure, such as sorted data or recursive patterns. Without specific problem details, adopting a layered strategy, starting with correctness and iteratively refining for efficiency, provides a systematic way to approach and solve algorithmic challenges effectively. To begin solving any algorithmic problem, the first step is to deeply understand the problem itself. Start by identifying the inputs. What kind of data is provided? Is it an array, a graph, or maybe a string? Then determine the expected outputs. Are you returning a single value, a subset of the input, or perhaps a modified data structure? Next, examine the constraints. For example, there might be limits on the size of the input, like n being less than 10,000, or guarantees about the data, such as arrays being sorted or having unique elements. Finally, think about edge cases. These could include scenarios like empty inputs, the smallest or largest possible values, or duplicate data. Understanding these aspects ensures you have a solid foundation before diving into the solution. Once you grasp the problem, the next step is to explore a brute force solution. This involves the most straightforward approach, where you iterate through all possibilities to guarantee correctness. It provides a baseline for optimization. For instance, if the problem asks you to find pairs in an array that sum to a specific value, a brute force method would involve nested loops to check all possible pairs. While this may not be efficient, it's a reliable starting point. Now that you have a brute force solution, the next step is to optimize by looking for patterns in the problem or the data. For instance, sorting is a common technique that simplifies many problems, such as finding pairs, subsets, or merging intervals. Hashing is another powerful tool. Using hash maps or sets can drastically reduce computation time by enabling faster lookups. For example, instead of iterating through pairs to find a sum, you can store values in a hash map and check for complements in linear time. Another effective technique is the two-pointer approach, particularly useful for problems involving sorted arrays. Once patterns are identified, it's crucial to choose the right data structures for your solution. Arrays are great for fixed-size data and fast random access. Hash maps or sets are ideal for tasks like frequency counting or checking existence, thanks to their average O(1) lookup time. If the problem involves dynamically retrieving the smallest or largest elements, a heap or priority queue is often the best choice. And for graph-related problems, adjacency lists or matrices are essential tools. For example, if you need to find pairs in an array with a specific sum, you might use a hash map to store values and their indices, enabling a quick O(n) solution. After selecting your optimal approach and data structures, the next step is to implement and thoroughly test your solution. Start by writing clean, modular code that's easy to debug. Then, test it against a variety of cases. Begin with small and simple examples to confirm the basic correctness of your algorithm. Follow this by testing edge cases. These might include empty inputs, extremely large or small values, or other unusual scenarios that could lead to issues. Finally, evaluate your solution with large test cases to ensure it performs efficiently under the given constraints. Throughout this process, it's important to keep a few key insights in mind. While brute force solutions are simple and guarantee correctness, they are often too inefficient for larger inputs. Optimized algorithms aim to strike a balance between clarity and performance. Additionally, many optimization techniques, such as sorting or dynamic programming, are reusable across different problems. Always consider edge cases to prevent runtime errors and ensure robustness. Selecting the right data structures, such as hash maps for frequency counting or priority queues for dynamic retrieval, can also significantly enhance the efficiency of your solution. To further refine your understanding, let's discuss key operations that frequently arise in optimized algorithms. Sorting is one of the most common techniques and is often the first step in reducing complexity, typically with a time cost of O(n) log n. Binary search is another powerful tool, especially for sorted data, allowing you to locate elements in just O log n time. Dynamic programming is invaluable for problems that can be broken into overlapping subproblems, as it avoids redundant computations and improves efficiency. To illustrate these concepts, consider a problem where you need to find the maximum product of any three numbers in an array. The input is an array of integers, and the output is this maximum product. First, sort the array. Then, evaluate two scenarios, the product of the three largest numbers, and the product of the two smallest, negative, numbers combined with the largest number. The result is the maximum of these two values. This method leverages sorting to simplify the problem, resulting in a time complexity of O(n) log n. By following this structured approach, you ensure that your solution is both clear and efficient, while also accounting for edge cases and constraints. The problem description for LeetCode problem number 1789 is not available, which prevents generating a specific solution. A placeholder Python class has been provided, which can be updated once the problem details are clarified. This class includes a method named solve, which would house the logic for the solution once the inputs, outputs, and constraints are defined. This is the Java implementation of the solution, based on the provided Python placeholder. The class structure is defined with a solve method that takes a string parameter, mirroring the Python logic. Key differences include Java's type declarations and class structure. Once the problem details are clarified, you can implement the specific logic within the solve method. In this first example, we are given the input data as a list containing the elements 1, 2, 3. To solve the problem, we begin by initializing a solution instance and calling the solve method with this input. The method starts by setting up a variable called total_sum with an initial value of 0. Next, we process the input list by iterating through each element. First, we add 1 to total_sum, which updates its value to 1. Then, we add 2, bringing the total to 3. Finally, we add 3, resulting in a final total of 6. After completing the iteration, the calculated total_sum is returned as the output, which is 6 for this example. The output for the first example is confirmed to be 6. Now, in the second example, we explore how the method handles an empty input list. When the solve method is called with data equals, it again initializes total_sum to 0. Since the input list is empty, there are no elements to iterate over, so no additions are performed. As a result, the value of total_sum remains unchanged at 0. This value is then returned as the output, which correctly represents the sum of an empty list. The final output for this case is 0. In the third example, we test the solution with a more complex input list that includes both positive and negative numbers. The input data is 5, -3, 8, -2. The method starts by initializing total_sum to 0 as before. Then, we proceed to iterate through the list. First, we add 5 to total_sum, resulting in a value of 5. Next, we add -3, which decreases the total to 2. Adding 8 increases the total to 10, and finally, adding -2 adjusts the total back down to 8. This step-by-step processing ensures that all elements, including negative numbers, are correctly accounted for in the calculation. After completing the iteration over the input list in the complex case, we find that the final value of total_sum is 8. This value is returned as the output, representing the sum of all the elements in the list, 5, -3, 8, -2. The output for this example is confirmed to be 8, demonstrating that the solution correctly handles lists with both positive and negative values, as well as varying lengths and compositions. In this section, we explore the concept of time complexity as it applies to problem number 1789. While the exact details of the problem are missing, we can outline the general process for analyzing time complexity. First, it's important to identify the operations involved in the algorithm. These could include loops, recursive calls, or other operations like sorting or searching. Each of these contributes differently to the runtime. Next, we define the size of the input, often denoted as n. The operations we just identified are then evaluated based on how they scale with respect to n. For example, a single loop iterating through an array is O(n), while nested loops might lead to O(n²). Finally, the total time complexity is determined by combining the contributions of all these operations. This structured approach helps us estimate the computational cost of an algorithm once all problem details are clarified. Now let's turn to space complexity. Similar to time complexity, analyzing space requirements involves understanding the algorithm's behavior. The first step is to assess how much additional memory is required for input storage or data structures like arrays, hash maps, or stacks. Additionally, if the algorithm uses recursion, the depth of the recursive call stack must be considered, as it directly impacts space usage. Finally, we account for auxiliary space, which refers to any temporary variables or data structures created during the execution of the algorithm. Together, these elements determine the overall space complexity. Without knowing the full problem description, it's difficult to provide exact estimates, but these general principles form the foundation for analyzing space requirements. A complete analysis would also allow us to compare an optimized solution against a brute force approach, helping to highlight efficiency improvements in both time and space usage. It's important to note that a complete complexity analysis requires the full problem description, including details like the input size and constraints. These are essential for accurately calculating the Big O notation for both time and space complexities. Without this information, we can only outline the general methodology for such an analysis. Once the problem is fully detailed, it becomes possible to assess the computational efficiency of the algorithm, identify bottlenecks, and optimize the solution as needed. This structured approach ensures that we can deliver both accurate and meaningful complexity evaluations tailored to the problem at hand. When tackling algorithmic problems, there are several common mistakes to watch out for. First, misunderstanding the problem statement is a frequent issue. Many people start coding without fully grasping the requirements, which can lead to incorrect assumptions. It's vital to clearly define the input, output, and constraints before jumping into the solution. Another pitfall is ignoring edge cases. For example, does your algorithm handle inputs like an empty array, a single element array, or extreme values like the maximum input size? Overlooking these edge cases can lead to runtime errors. Efficiency is another major concern. A brute force approach might work for small inputs, but as the input size grows, such as n reaching 10 to the power of 5, inefficiencies become glaring. Carefully analyzing and optimizing the time and space complexity is essential. Additionally, selecting the wrong data structure can lead to inefficiencies. For instance, using a list instead of a heap for priority queue operations can unnecessarily increase the complexity. Finally, off-by-one errors are a common source of bugs and problems involving loops or array indexing. Make sure to double-check boundary conditions to avoid these mistakes. In an interview setting, there are specific strategies that can help you stand out. Recognizing patterns in algorithmic problems is incredibly valuable. Many problems share common patterns, such as sliding window, binary search, or dynamic programming. Identifying the correct pattern early on can guide you toward an efficient solution. Testing your solution is equally important. By running sample inputs, edge cases, and even stress tests with large inputs, you can ensure correctness and identify potential inefficiencies. During the interview, clearly explaining your approach is critical. Even if you don't arrive at the optimal solution, demonstrating a structured and logical thought process leaves a positive impression. Another effective strategy is iterative refinement. Start with the simplest solution, like a brute force method, and then refine it step by step to improve efficiency. Finally, be prepared to discuss trade-offs. For example, a faster algorithm might use more memory. Being able to articulate these trade-offs demonstrates a deeper understanding of the problem and potential solutions. To further develop your problem-solving skills, it's helpful to explore related problems. For instance, the two-sum problem, LeetCode number 1, focuses on finding two numbers in an array that add up to a target value. The three-sum problem, LeetCode number 15, builds on this idea by finding three numbers that meet the target, emphasizing sorting and two-pointer techniques. Another related challenge is the longest substring without repeating characters, LeetCode number 3, which uses a sliding window approach and requires careful management of indices and hash maps. For more advanced practice, the minimum window substring, LeetCode number 76, involves string manipulation and hash maps in a more intricate sliding window setup. Beyond solving these problems, it's important to consider alternative approaches. While brute force methods are simple to implement, they're often inefficient for larger inputs. Optimized algorithms, such as sliding window or dynamic programming, reduce time complexity but may require more memory and careful coding. Pre-processing techniques, like using prefix sums for range queries, can offer significant performance gains for repeated queries, though they often come with increased space complexity. Balancing these trade-offs can help you decide the best approach for a specific scenario. The most important takeaway for solving algorithmic problems is mastering a combination of skills. Start by deeply understanding the problem, including its constraints and requirements. Recognize patterns that can guide your approach, such as sliding window or dynamic programming. Apply appropriate techniques and ensure your solution is both correct and efficient. Testing your code thoroughly is non-negotiable. Cover all edge cases and run stress tests to validate your implementation. Additionally, always consider trade-offs between time and space complexity, showing that you can think critically about your solution. Lastly, focus on clear communication. Whether in an interview or collaborative setting, articulating your thought process and reasoning effectively can make all the difference in demonstrating your expertise. Great job! Today, we tackled a unique challenge with limited information, emphasizing the importance of adaptability in structured problem solving. Don't forget to practice similar problems and keep improving your skills. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!